This engine can lift over 200 pickup trucks at once. It burns fuel at 6,000 degrees Fahrenheit. Somehow, it doesn't melt. It weighs almost 4 tons. This is the engine that's sending humans back to the moon. Today, I'm breaking down exactly how this thing survives the most extreme conditions ever engineered. This is RS-25. NASA says the most capable rocket in the world is the Space Launch System, or SLS, and RS-25 engines are powering this rocket. That is unbelievable. The RS-25 is a cryogenic liquid rocket engine. It burns liquid oxygen and liquid hydrogen. It first flew as the Space Shuttle main engine, 3 at a time on every shuttle launch, completed 135 missions. You know, this engine is one of the most tested large rocket engines in history. Now it flies again on NASA's moon rocket, the Space Launch System. But this time, it's 4 engines together on the core stage. In space, an RS-25 engine can produce 512,000 pounds of thrust. That's like lifting over 200 full-size pickup trucks at the same time. Even at sea level, before the rocket leaves Earth, it still pushes with 418,000 pounds of force. And remember, 4 of these engines fire together on NASA's moon rocket. The RS-25 is about 4.3 meters tall, roughly the height of a 2-story building, and 2.4 meters wide. Big enough to stand inside, but precise enough to run like a watch. Each engine weighs around 3.5 tons. That's heavier than most cars, yet it's built to survive extreme heat, pressure, and vibration. The RS-25 doesn't just run at full power, it runs at 109% thrust. That extra margin gives engineers flexibility during launch, when every second counts. Each engine burns for about 8 minutes, just long enough to push the rocket from the launch pad all the way toward orbit. Before ignition, parts of the engine are as cold as -423 degrees Fahrenheit, colder than anything naturally found on Earth. Seconds later, inside the engine, temperatures soar to nearly 6,000 degrees Fahrenheit. That means the RS-25 handles the coldest cold and the hottest heat in the same machine at the same time. That's why the RS-25 isn't just powerful, it's one of the most extreme engineering achievements ever flown. Most rocket engines are basically pump propellant, burn it, and blast it out the nozzle. The RS-25 does that, but with a clever twist called staged combustion. Liquid oxygen and liquid hydrogen enter the engine. Before the main burn, tiny pre-burners partially burn propellant to create hot, high-pressure gas. That gas spins the turbopumps, the engine's turbocharged heart, at extreme speeds. Then everything flows into the main combustion chamber and exits through the nozzle as a focused, supersonic exhaust jet. The hot gas used to drive the pumps doesn't get dumped overboard, it joins the main burn. That's a big reason the RS-25 is so efficient. So why isn't every rocket engine like this? Because staged combustion means the engine operates at extreme pressures and temperatures, and it has to stay stable. If combustion becomes unstable, it can destroy an engine in milliseconds. The RS-25's turbopumps are especially intense. They push cryogenic propellants at enormous pressure, with precision sealing, tight tolerances, and materials that survive brutal thermal stress. And the combustion chamber? It's cooled using regenerative cooling. Fuel is routed through channels around the chamber and nozzle, absorbing heat so the metal doesn't melt. Think of it like running an icy river through the walls of a furnace, while the furnace is trying to explode. When the Space Shuttle retired, NASA still had RS-25 engines, and they were too valuable to ignore. For SLS, NASA upgraded them for the new mission profile. They introduced a new engine controller, basically the engine's computer brain, improving processing power and compatibility with modern systems. They also certified higher operating levels compared to typical shuttle flights. And because SLS uses 4 engines and different staging, the engine's operating environment, start sequence, and integration changed too. The RS-25 went from reusable engine flying many times on one spacecraft, to high-performance engines powering a heavy-lift rocket. The RS-25 isn't just an engine. It's a proof of what peak chemical rocket engineering looks like. High efficiency, deep throttling capability, reliable starts, and a heritage of real flight time. It's the kind of hardware that doesn't just push a rocket, it pushes the limits of what engineering can survive. That's why the RS-25 is still here, decades after its first roar, powering a new era of deep space missions. The planet didn't change. Physics didn't change. But the tools got better. And this engine is still one of the sharpest tools we've ever built.